Now, when we're talking about the gases, it's important to look at volume, pressure, and temperature. And so, we're looking at, the state of that system, and we're looking at, what's going on with that gas. And we're going to deal with gases that aren't too dense. And so we're dealing with ideal gases that are not too dense, and they obey the ideal gas law relationship that we're going to look at. So with this one here, K5A, let's say that we have an ideal gas, and let's take a look at the properties of this gas, with an ideal gas. So it cannot be liquefied or solidified. And so, like real gases, and molecules obey the laws of mechanics, and so they obey Newton's laws. The molecules are point particles, and they each have negligible volume. And when they collide with the walls, the collisions are elastic. They're elastic collisions. The molecules have a range of speeds, and they move randomly as well. And so this is true. All these are true with ideal gases. And a real gas may be approximated by an ideal gas as long as the density is low. And so if you have too dense of a gas, it's not really going to obey what's going on with the ideal gas law here. Okay, so if you want to pull up the simulation, you can go to PhET and then go to gas properties. And then let's take a look at what would happen to pressure if volume is changed but the temperature remains the same. And so when you do that simulation and you try that, you can see what happens. And what you'll see is what happens in one of these properties that we're looking at, gas properties. And so go ahead and pause the clip, give that a try, and when you're ready to learn more about that, you can hit play, and then we'll take a look at it here. Okay, so with Boyle's law then, we're dealing with an inversely proportional relationship. The volume and the pressure, as long as temperature is constant, is inversely proportional. So in other words, as the volume gets bigger, right, as we get bigger in volume, pressure is going to drop. And as pressure drops, if we keep temperature the same, that's what will happen there, and that's Boyle's law. So volume is inversely proportional to pressure in Boyle's law. What we're going to be using for volume is meters cubed, and then pressure is going to be in newtons per meter squared. And then also pascals. That's what 1 Newton per meter squared is 1 Pascal. Okay, so this is Charles' law. What happens with Charles' law? The volume is linearly proportional to temperature. And this is where the pressure stays constant. So the volume is proportional to temperature. So in other words, as the temperature decreases, right, as we get 200 degrees, 100 degrees, 0 degrees, the volume is getting smaller and smaller and smaller and smaller, till theoretically where the volume would be 0, and that would be at 0 Kelvin. And so we know that we're not going to have 0 volume. Some really weird things happen around absolute 0, and in fact they just went below absolute 0 not too long ago. And so that's significant there with, but this should make sense, right? You have a the volume is getting smaller and smaller and smaller. The temperature is getting colder and colder and colder, so the volume is getting smaller and smaller and smaller as we go to keep the pressure the same, right? Okay. So temperature being Kelvin, volumes in meters cubed, and we can. All right, so in this one, we'll practice this here. This is case 7. An ideal gas is in a sealed container with movable top. Person changes the volume from 0.0187 meters cubed to 0.00973 meters cubed. If the original temperature was 16 degrees Celsius, what is the final temperature in Kelvin? And the pressures kept same throughout the change. So what I want you to do is go ahead and set this up, gas before, gas after. All right, we'll get this into Kelvin here. So gas before, gas after. See if you can solve for the final temperature. in Kelvin. And so once you do that, you can hit play to continue. So go ahead and pause, and then we'll take a look at it. All right, so pressure is the same from both sides, so we can divide both sides by pressure, divide both sides by the number of moles of gas, so that's not changing, and then the gas constant's not changing, so we end up with a ratio of volumes and temperatures, and we should get a temperature of 150.37 Kelvin, so that should be the final temperature. In Kelvin, the initial temperature was 289, okay? And so to keep the same amount of pressure, as this compresses here, the temperature's got to drop to keep the same amount of pressure. So what you can consider with this is, for instance, let's say you had a container like this, a metal container that's a fixed volume, right? And the volume's not changing. So if you keep heating this up and the gases are moving faster and faster and faster inside here, right? Eventually, right, it can be, you can get very, very high pressure. And then if something's wrong where the pressure gets so much, you can have an explosion where one of these valves, if the pressure builds up too much, maybe it'll explode. And so, as you're dealing with higher and higher and higher pressures, it takes more and more, integrity of the structure to be able to withstand that. So I show in this clip, an oil tank explosion where, the pressure built up so much that eventually the structure gave way and explodes. So this is the Gay-Lussac's law, where the volume is constant, pressure is directly proportional to temperature, and the pressure is in pascals, temperature. Okay, so an ideal gas is in a sealed container with a fixed volume. Person heats up the container so the temperature goes from 293 Kelvin to 310 Kelvin. What's the corresponding increase in pressure if the original pressure was 241 pascals? So I want you to go ahead and set this up. Go ahead and draw it out and set up your variables and see if you can figure out what the increase in pressure will be. And again, you're looking at the ideal gas before, ideal gas after, and seeing what cancels out from both sides and doing that. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we've got our gas, temperature 1, 293, temperature 2, 310, pressure 1, 241 pascals, and we can cancel volume from both sides. Volume's fixed, so same volume on both sides, same number of moles on both sides. Ideal gas constant's the same for both, so we're looking at a ratio of the pressures and temperatures, and we end up getting a pressure of 254.98 pascals. All right, so as we talk about quantity of gas, what's going on with gas, the mole is a really helpful thing that we use. And so go ahead and draw a box representing a gas inside this box. And inside this box, if this is 1 mole, you have many, and it's actually a fixed number of molecules. And that value is 6.02 times 10 to the 23rd. That's a lot of them inside, okay? Now, let's do an example. Let's say that we have helium. And let's say that helium 2, okay? So they're together. Now, what does that actually mean? You have a helium nucleus, so plus, neutron, plus, proton, neutron, okay? You have the electrons. Actually, 1, 2, 3, 4, 5, 6, 7, 8. Now, what makes a molecule? A molecule is where you have 2 nuclei sharing electrons. So let's say that this right here represents helium-2, right? And that is one of these black dots. So there are 6.02 times 10 to the 23rd of them. There are many of these, okay? Now, that is a mole. We have 1 mole of them. And, of helium. Now, let's go ahead and add this one here. What is the mass of 4 moles of nitrogen gas? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we have, nitrogen N2, which would be 14 times 2. And so that's 28 U. So 1 mole of that would be 28 grams. We have 4 moles of that. So we have 112 grams of nitrogen gas for that. Okay, now the mole. The mole is defined as the number of grams of a substance that is numerically equal to the molecular mass of the substance. So in other words, if we had 1 mole of H2, right, 1 mole, so here's a container, and in this container we have a lot of these molecules, right, a very specific amount, we'll talk about that. And then H2 has a mass of 2.02 grams. So that is how much, if we had a gas, right, this gas, and we put it on a scale, and we would read that, we would have 2.02 grams is how much that would be. And the way we got that, if we know what hydrogen is, this is 1.0079 U, right? We have 2 of those. We have the corresponding grams. And so in other words, like with this, we have this is U for neon, right? That's the atomic mass. So therefore, if we have a mole of that, right? And so I should kept it the same size as this, right? So same size, and we have all of those neon molecules inside, right? 1 mole of that, 1 mole of neon is this many grams. And so if we put it on a scale, we would read 20.1797 grams because of all those different molecules in there. If we have CO2, it's 1 carbon, oxygen, 2 oxygen atoms, right? So we add those up in U, and so that container would have, we measured it, would have 44 grams of mass. And that should make sense because every mole has the same number of molecules, the same number of dots. There's the same number of dots in here, same number of dots in here, same number of dots in here. Each dot represents 1 molecule. And so therefore, if you have the same number of molecules, each molecule has a different amount of mass. And so therefore, if you have the same number of CO2s as you have H2s, right, you're obviously going to have more mass. And so that's what we're dealing with there. So the number of moles in a certain mass is, or the number of moles in a certain mass of material is this relationship here. And so hopefully that makes sense there. Okay, so let's take a look at this for F10. And let's say we want to find out the mass in grams of 3 moles of fluorine gas. So here is 1 mole of it. Here's another mole of it. And here's another mole, right? So in these 3 moles, how much mass is there? How much mass? And so in fluorine, right, fluorine is F2. And so we can do that. So if we want to know how many molecules there are, and here's Avogadro's constant, this is the number I was alluding to earlier. In 1 mole, right, if you have this gas inside, you have all these dots, each of these dots represent a molecule, okay? In a mole, in 1 mole, this is how many molecules, that's how many dots you have. That's how many dots you have. So if you have H2, let's say, right, H2 gas, then that's how many H2s you have in there, right? Or fluorine, right, fluorine gas, F2s, that's how many F2s are in there. And so this is the total number of molecules in 3 moles, right? And that's for any gas, right? So it could be for H2, for F2, oxygen, 8O2, whatever, okay? So once we have that, we know that we can multiply that by 2, and for 3 moles, right? So 1 mole would be that. That would be how many molecules are inside. So in other words, that's how many dots you have in there. But every single one of these dots, if we look at one of these dots, that means that we have 2 atoms of fluorine, right? So if we have 2 atoms of fluorine, this is the total number of atoms. We have to multiply this by 2 because each of these dots again just represents F2, which are 2 separate atoms that are sharing electrons, right? So that's the total number of atoms. And then if we know that, and we know that fluorine is this value in U, we multiply that by U, and we get that mass, and then we can convert that to kilograms. Now, what's easier than that is just noting that, okay, you know, in 1 mole, right, in 1 mole, we have this many grams. But the trouble is it's F2, right? So we would multiply this by 2, and that's how many grams that we would have. And so that's a little bit easier way to go about it, but it's important to know both ways. So when we take a look at the ideal gas law, PV equals nRT, where N is the number of moles, R is the gas constant here. And this is the typical unit that we'll use. We're dealing with Kelvin, right, for temperature. Joules, with joules, you're going to be dealing with meters cubed for volume, pascals for pressure. And so this is typically what we'll use there. Okay, so 3 moles of CO2 are enclosed in a sealed container, 40 centimeters by 25 centimeters by 15 centimeters. If the pressure is 1 atmosphere, what is the temperature of the gas in the container? So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so here's our gas, PV equals nRT. 1 atmosphere is 101,000 pascals. Technically 101,300. Either way is going to be okay. It's going to be plenty close. The volume is 0.015 meters. That should be meters cubed, not meters squared. We'll set everything in there. And we should get a temperature of 60.73 Kelvin. So this would be very, very, very cold if this was the actual situation there.